Hi, everybody. My name is Kilian Schlager. I'm an earthquake engineering student, undergraduate at Rutgers. So this is going to be a little bit less technical. You can rest your brains for it. And this summer I worked with Dr. Moore and Molly Watts on the T-Finder project. Specifically, the scope of my project was designing and manufacturing the graphite disc and sail assembly for essentially a mini thruster of what hopefully the larger scale project is going to be. Specifically, I was working on the current mitigation within the graphite, which I'll elaborate more on later. So then I'm going to give a breakdown of T-Finder, a little bit of background, and then jump into the design, simulation, and manufacturing this. So what is T-Finder? Well, for those of you who are familiar with solar sail, T-Finder is very similar. It's essentially like the brainchild of the solar sail. So rather than using photons to propel ourselves through space, we're using alpha decay. So we're getting a lot more energy from the alphas than we would from photons, but we're keeping all of that efficiency that we do get from a solar sail. Where we're doing this is we're coating one side of a sail essentially with a radioactive isotope that's then emitting alphas only through one side and blocking through the other, which allows us to get that high thrust. The application of this is mostly used like deep space, so we can think like intercepting interstellar objects that might be coming through our solar system, or even solar gravitational focus experiment, just essentially taking a telescope, putting it super far out in the solar system to a point where we can actually use the gravitational work of the sun to magnify deep space. The neat feel of this is that with conventional rocketry, it would take us around 130 years to get there, versus the T-Finder, we could actually do that in 26. So it's really allowing us to make these massive leaps within our lifetime. Unfortunately, we can't just dump billions into T-Finder just yet, so we have to do a proof of concept first, which is what this mini thruster is, and what we're working on here at Yale, as well as in collaboration with Northwestern and Draper up in Boston. So what you see here is a model of what we had in the lab, essentially just a magnet with a graphite disc and a sail on top, which we hope to embed our radioactive isotope in the alps eventually. The idea of this is, again, proof of concept. We want to also measure and get a sense of how much thrust we could actually achieve from a larger scale model. But since we're working with such small forces, any damping or any noise we're getting in the system means that we're getting massive margins of error. Specifically, eddy currents have been our biggest problem right now. Now, in a lovely system, it should be all axially symmetric, which means that we get no changing flux and no eddy currents, but that's not how that works. So any slight issues in the manufacture of this, or a misalignment between the gravitational and magnetic fields, mean that we do get some vibration and ultimately flux through our disk. So the eddy currents have been so far a pretty big problem. And the Twomley group, they did a similar experiment, not really T-Finder related, but they did actually do measurements in terms of the actual displacement from the center and how that correlates to our damping rates. And it is pretty significant. And on the right here, you can see our setup. It's pretty simple. It's a vacuum pump with some imaging lasers. And then the bottom, we have a tilt stage, just try and line up gravitational fields as best as possible. So the project goal workflow is pretty simple. It's kind of a marriage between design and simulation, which then kind of culminated into a final design fabrication. I'm going to talk about the eddy a little bit in this presentation. It's just a metric that we use to quantify like how much density of the eddy currents we're getting in the graph. Or in our disk, sorry. The design process was fairly simple. It was to take 5 or 10 kind of entirely unique designs, see what gives us our lowest p-eddy value, and then basically stick with that one and optimize that as much as possible. So here you can see roughly 10 different designs that were tried. The yellow ones are benchmark designs. So if you look at all the way on the left there, we have a blank disk, which is exactly what it sounds. It's a recessed, or it's a blank disk with no recessions. So we get the highest eddy currents in there because there's nothing to break up those current pathways. In the middle, we have the Twomley disk, which is that other group that I mentioned, and their disk was sufficient for their experiments, but not sensitive enough for ours. And then Dr. Moore did a preliminary recession disk before I arrived, which is that middle yellow one. And then all the way on the right here, we have the Snowflake series, which was the kind of crux of the project here and what we ended up using. So this is the final Snowflake series. Ultimately, it was the best disk that we came up with console simulations. and it was a 98% reduction to the blank disc and 73% reduction to Dr. Moore's risk. And these are 5 different iterations of this, probably about 20. But this was ultimately we landed on version 1.3, which was a fairly significant reduction simulation-wise compared to the blank disc. The next major step was fabrication. So our initial cuts, as you can see on the top left there, were crude to say the least, and often took upwards of 20 minutes to laser cut. But through the optimization of the CAD file, as well as some of the parameters in place, we managed to actually cut that down to 90 seconds. And the big one was our yield improvement. It went from about 5% to 95%. So we kind of flipped that on its head and managed to get 19 out of 20 cuts are now useful, which is great. We also did some location tests, different radius, different radii, different thicknesses, and even different cutouts of the discs. And we actually found that the measured gap, which we measured with a pixel software, was identical between all the discs, and nearly identical between all the discs, which we chalked up to surface area relation and weights between the magnetic field. Finally, the sail design was the last component related to the assembly. Had some unique constraints because it had to be light enough that we wouldn't change really the rotational inertia of the assembly, but at the same time dense and thick enough to actually stop those alphas from permeating. So what we ended up using was aluminum 1100, about 100 microns thick, so pretty thin, but actually surprisingly rigid. And then that was married to the graphite assembly using silver epoxy. And then on the top up there, you can see kind of the final drawing of what that sail looked like. For reference, I don't know if I've mentioned, but the disc is 3 millimeters in diameter, so it's a pretty small assembly. It's just big enough to see and just small enough to be annoying to work with. And yes, so these are the final assemblies and how they came out. We managed to get 4 assembled disc sails, probably about 25 attempts. The hardest part was definitely marrying the two together. As you can imagine, putting a 3 millimeter sail into a slot that's like thinner than your fingernails takes time. But yeah, ultimately the rotational half-life. So when we spin up that disc, the rotational half-life in terms of how long it takes to get to half its speed is measured around 14 hours. We haven't actually been able to experimentally confirm that yet, but that is hopefully the next step, which is a pretty big improvement to the 20 minutes that the blank disc sat around. And yes, big thank you, Dr. Moore and Ollie. Thanks for trusting me with your lab and taking me on. And yes, thank you guys for listening, and I'll take any questions.
Great talk. Can you explain the snowflake design of the velocity?
Yeah, sure. So the interesting thing we actually ended up seeing in console simulations is that our top surface and bottom surface were exhibiting different eddy current patterns. You can see it a little bit here. So the bottom surface would all kind of conglomerate bottoms in the center versus the top, which would go radially outward to like the furthest kind of complete circle that it could go. We went through a bunch of different stuff, and the interesting thing is, I would have thought that rounded shapes, as in like circles, would give our best eddy current mitigation because you have no edges for that, that field and that charge to accumulate. But what ended up happening was at a certain level of rounding, they actually started to pick back up instead of die down. So hexagons were a really nice medium in terms of getting that balance between too sharp and too round. And then it was really just playing around with the different configurations of hexagons that kind of ended up with the snowflake.
This is a neat design. Do you imagine it having applications beyond like the test with the people?
What do you mean in terms of? Do you like elaborate on your questions?
Another or I guess you're using it for this rotation of the.
Yeah, it's to mitigate the current so that we can get a better idea, kind of a more stable torque, really. Yes, absolutely. That is definitely more towards Dr. Moore's, I think, area of expertise here. As I said, I don't understand any of the neutrino magic that goes on in his lab, but I have been told that this could be potentially useful here.